Survey of Calculus, Chapter 2, Section 5, Maximum Minimum Problems, Business and Economics Applications. Okay, so here's our strategy for solving these problems. First of all, read it carefully, and if necessary, if relevant, if it's going to help, make a drawing. Then you want to make a list of appropriate variables and any constraints, noting what varies, what stays fixed, and what units are used. Label the measurements on your drawing if you made a drawing. Next, translate the problem to an equation involving a quantity to be maximized or minimized. Try to represent that quantity Q in terms of the variables that you came up with in step 2. And try to express it as a function of one variable. Use the procedures that you've developed in the chapter this far to determine the maximum or minimum values and the points at which they occur. In other words, use the first and second derivative rules. So here's an example. We have a thin piece of cardboard. It's 8 by 8. Square corners are going to be cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume, and what is that maximum volume? Okay, you've actually done these cardboard box problems before. A drawing is very helpful. Pause the recording, give it a try, and resume to see how you did. Okay, so here we have our drawings. The first drawing shows the piece of cardboard itself with the dotted lines for where we're going to cut out our squares. We don't know the dimensions of the squares, so we will label the sides of the little squares we're going to cut out as X. And then we note that what that's going to do is it's going to reduce the length of the piece of cardboard, the size of our box, to 8 minus 2x, because you'll take x out from each side. The second drawing shows what the box will look like once we have folded it up. And you'll notice that the bottom, the length and the width of the bottom is 8 minus 2x, and then the height will be x. It's determined by how much you cut out. Write an equation. Volume is length times width times height. So using the dimensions that we just discovered in our drawing, 8 minus 2x times 8 minus 2x times x. They went ahead and squared it here, so we have 64 minus 32x plus 4x squared times x. And then if you distribute and put everything in descending order, you have that the volume of our box is 4x cubed minus 32x squared plus 64x. Now, x needs to be between 0 and 4 because the square piece of cardboard we start with is only 8 inches from each side. And if you take off, well, you can't take off more than 4 because more than 4 will cut off more than just the side length. So x cannot be more than 4. In fact, you don't want it to be 4 because then you'll just cut the side length off, and it's got to be greater than 0. So our volume is going to be maximized on the open interval from 0 to 4. So we take the derivative and set it equal to 0. And here we have divided everything by 4 and factored. And we get that 3x minus 4 is 0, or x minus 4 is 0, which gives us 4/3, or 4. Now, we just said that we can only use values between 0 and 4, so 4 cannot be included, which means we can only use 4/3. Since it only has one critical value, we can test it with the second derivative. The second derivative is 24x minus 64. And putting in 4/3, we get that it is a negative second derivative, which means that we do have a maximum. So the volume is maximized when the square corners are 4/3 inches. And the volume we get by putting 4/3 into our original formula, and we get that the volume of the box is going to be 3725 over 27 cubic inches. Try another one. It's going to be a repeat of the last one. Our cardboard this time is going to measure 8.5 by 11, so the size of a sheet of notebook paper. And the question is, will it hold a liter of liquid? And they're telling us that a liter is 1,000 cubic centimeters, and 1 cubic inch is 16.38 cubic centimeters. So pause the recording, give this a try, and resume to check your answer. Okay, you could even go back to your drawing for example 1 because this is really, all we're going to do is change the 8s to 8.5 and 11. So we get our dimensions of 8.5 minus 2x, 11 minus 2x, and x. We also have to redefine our interval that we're going to maximize on. It still has to be greater than 0, but this time it's going to have to be less than 4.25, and that's 4.25 is half of 8.5. So here we have our equation, and we've multiplied it all out. And then, like I just said, our sides have to be greater than 0, which means that for the 11, the side that's 11 inches, our x has to be between 0 and 5.5. But for the smaller side, it has to be between 0 and 4.25. So we need to use that smaller interval. Now this one cannot be factored, and so we're going to use the quadratic formula on it. And we get 4.917 or 1.585. 4.917 is not in our range, so we're going to use 1.5. Then we're going to check our second derivative. It is indeed negative, so that tells us that this is a maximum. And the dimensions are about 1.585 by 5.33 by 7.83. That gives us a volume of 66.15 cubic inches. Converting that to cubic centimeters, we get 1,083.5 cubic centimeters, which is greater than a liter because a liter is 1,000. So the box could hold 1 liter of water. Next example. A stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit must be P of X is 1,000 minus X, and the cost of producing those units is 3,000 plus 2X. You're going to find the revenue. And remember, revenue is the amount of money that you bring in. So it's how much you're selling it for times how many you sell. Profit is revenue minus cost. How many units does it have to produce to maximize profit? What is the maximum profit, and what price must be charged? Pause the recording, give these a try, and resume to check your answer. Okay, so revenue is quantity plus times price. Quantity is just X. Our price is 1,000 minus X. So 1,000X minus X squared, that's our revenue. Our profit is revenue minus cost. So again, we're going to set up a little problem here, subtract. Don't forget to distribute that minus sign, and we get negative X squared plus 980X minus 3,000. Then we take the derivative of profit, and we set it equal to 0 because that's going to tell us where the maximum profit is. And solving, we get that when you have sold 490 units, you are maximizing your profit. Well, assuming it is a maximum. So we do need to check and see if this is going to be a maximum or minimum. When we take the second derivative, we get negative 2, which is negative. So that is indeed does indeed tell us that X equals 490 is a maximum. So when X is 490, our profit is maximized. And our maximum profit is found by putting 490 into our profit function, and we get $237,100. So they make a maximum profit of $237,100 when 490 units are bought and sold. The price per unit to achieve this, now we need to figure out what P is. Well, we know what X is, so the P of 490 is $510. We're going to try that same problem, different price and different cost functions. So repeat what you just did with these two new functions. Pause the recording, give it a try, and resume to check your answer. First, we find the revenue. And then we find our profit. And then we take the first derivative of profit and set it equal to 0. We get that X is 433.75. And then we test to see if that's a maximum or minimum. I know this is a little dark here, but when we take the second derivative, we get negative 4, which is negative. So that is going to be a maximum. Now we do need to round up to 434 units because you can't sell 3/4 of a unit. Then we find our maximum profit. So our maximum profit is $374,028. The price per unit is, we're going to put our 434 into our price function, and we get $882. Okay, Theorem 10. Theorem 10 tells us that maximum profit occurs at those X values for which the derivative of revenue equals the derivative of cost, and the second derivative of revenue is less than the second derivative of cost. So we want the two derivatives to equal each other, and that's going to give us maximum profit. Which makes sense, because think about this. How do you find the profit? You do revenue minus cost. And then you take the derivative and set it equal to 0. Well, if you were to just take the derivatives of the two functions and then, add the cost to both sides, you would have this little equation here. All right, one more example. Promoters of an international fundraising concert must walk a fine line between profit and loss, especially when determining the price to charge for admission to closed-circuit TV showings in local theaters. By keeping records, a theater determines that at an admission price of $26, it averages 1,000 people in attendance. For every drop in the price of $1, it gains 50 customers. Every customer spends an average of $4 on concessions. What admission price should the theater charge in order to maximize total revenue? Okay, you've got a lot to think about here. See if you can kind of work out how this is going to look. Pause the recording, give this a try, and resume to see how you did. Okay, so X is going to be the number of dollars by which we reduce the price. So the revenue is going to be revenue from tickets plus concessions, so we've got two sources of income here. The revenue is going to be the number of people times the ticket price plus the number of people times 4, because they spend $4 per, on average per person for concessions. Okay, the number of people, it's 1,000 plus 50x, because every time they reduce the price by $1, they gain 50 people. So X would be the amount of money you're reducing the ticket price by. So 1,000 plus 50x times 26 minus X. Again, X being what you're going to reduce the ticket by. Plus 1,000 plus 50x, that's the number of people again, times 4. Put all the numbers in and simplify, and we get this equation. We want to find the derivative of revenue and solve for critical values. So the derivative is negative 100x plus 500. And solving, we get x is 5. So 5 is our critical value. We can try the second derivative to determine if there's a maximum or minimum. And it is negative, so that is a maximum. 5 is our maximum. So x equals 5 yields a maximum revenue. So the theater should charge $21 per ticket. All right, same idea here. Give this one a try. Follow the pattern we just did. See how you do. Pause the recording. Resume when you're ready to check your answer. Okay, there's our revenue function, very similar to the previous one. Simplify. Okay, so we take our derivative and set it equal to 0 and solve for x, and we get 6.5. Then check our second derivative, and we see that it is negative. So x equals 6.5 will give us our maximum. Then we put x back into the formula for ticket price, and we find that they should charge $23.50. Okay, here's the summary of this section. You might want to pause and look over it, and then resume when you're ready to continue. Okay, the rest of this is some additional practice. So pause the recording, give these problems a try, resume when you're ready to continue, and do this through the rest of the recording.